Take a deep breath in, letting the cool air fill your lungs, and as you exhale, allow your body to settle completely into the quiet of this moment. Tonight, we are leaving the confines of Earth to float outward into the great comforting void, to witness the slow and majestic awakening of a new sun. Within the sweeping spiral arms of our Milky Way galaxy lie immense, silent sanctuaries known as giant molecular clouds, the true stellar nurseries of the cosmos. Here is something remarkable to ground our journey. These dark, sprawling veils of matter are unimaginably vast, often spanning anywhere from 10 to 100 parsecs across. To put that magnificent scale into perspective, that is roughly 30 to 300 light-years in diameter. And if you were to travel at the speed of light, zipping through the dark at 186,000 miles every single second, it would still take you 3 centuries just to cross from one edge of this nursery to the other. As you drift into the outermost edges of this molecular cloud, the first thing you might notice is the profound, beautiful chill. This is not a harsh cold, but a deep, preserving stillness. The temperature within these clouds hovers between 10 and 20 Kelvin. In familiar terms, that is about 263 degrees below 0 Celsius, or minus 441 degrees Fahrenheit, just a breath away from absolute zero. This extreme, frigid environment is an absolute necessity for creation. In warmer temperatures, gases move with frantic, chaotic energy, refusing to bind together. But in this deep, quiet cold, the atoms are soothed. They slow down. They become sluggish and calm, allowing the gentle hand of gravity to finally gather them close. You might wonder what it feels like to move through this space. It is deeply peaceful, composed of 99% gas, mostly primordial hydrogen, with a scattering of helium left over from the dawn of time. The remaining 1% is cosmic dust. But this is not the dust you know on Earth. These are microscopic, jewel-like grains, forged in the dying breaths of ancient stars, made of heavy elements like silicates and pure carbon. Because the environment is so exceptionally cold, each of these tiny dust grains is wrapped in a smooth, microscopic mantle of frozen water, carbon monoxide, and ammonia ice. Imagine gliding your hand through a frictionless mist of microscopic ice diamonds, suspended perfectly in the dark. As you float deeper into the nursery, the texture of the space around you is lighter than the most delicate breath. A typical molecular cloud has a density of only 100 to 1,000 molecules per cubic centimeter. For comparison, a single cubic centimeter of the air you are breathing right now, resting in your room at sea level, contains about 25 quintillion molecules. By earthly standards, this cosmic cloud is a vacuum more perfect than any we can create in a laboratory. Yet, on the scale of the universe, this space is considered heavy, pregnant with the potential for light. For millions of years, this cloud simply drifts, resting in a state of quiet equilibrium. But the cosmos is a web of interconnected events, and soon a gentle disturbance ripples through the dark. It might be the shock wave from a distant supernova, a star that ended its life thousands of years ago, or a subtle shift in the gravitational tide as the cloud passes through a galactic spiral arm. This shock wave washes over the cloud at speeds of thousands of kilometers per second, a silent, invisible tide that compresses the gas and dust. As the wave passes, you can sense the shift. Certain pockets within the cloud become slightly more crowded, slightly denser. This triggers a fascinating mechanism of physics known as the Jeans instability. Formulated by the brilliant British physicist Sir James Jeans in the year 1902, this principle describes the exact critical mass required for gravity to finally overpower the internal pressure of a gas cloud. Once a pocket of gas crosses this specific threshold, the outward push of the cold atoms is no longer strong enough to resist the inward pull of their collective weight. And so, the long, slow collapse begins. You are now observing a pre-stellar core, an isolated fragment of the greater cloud that has decided to draw inward, retreating from the vastness to build something profoundly new. The process is remarkably patient. The initial phase of this gravitational collapse, known in astrophysics as the freefall time, unfolds with a majestic lack of urgency. For a typical star-forming core, this silent inward drift takes anywhere from 100,000 to 500,000 years. There is no rush. You can simply relax into the deep time of the universe, feeling the slow, rhythmic drawing together of matter. As the pre-stellar core shrinks, another fundamental law of the universe takes hold: the conservation of angular momentum. It is the exact same principle that causes an ice skater to spin faster as they pull their arms in close to their body. Because the original giant molecular cloud was already rotating at a glacial, imperceptible pace, this small, shrinking core begins to spin faster and faster as it condenses. You can feel the rhythm of this cosmic dance changing. The gentle inward pull becomes a swirling vortex. Centrifugal forces take effect, fighting against gravity at the equator of the spinning sphere. As a result, the falling gas and icy dust do not form a perfect ball. Instead, the material stretches outward, flattening into a magnificent glowing structure known as a protostellar disk. Gliding above this disk is a breathtaking experience. It is a sweeping, rotating plateau of matter that can span up to 1,000 astronomical units in width. 1 astronomical unit, or AU, is the average distance between the Earth and our Sun, about 93 million miles. This means this spinning platter of cosmic dust and gas is 1,000 times wider than the distance from Earth to the Sun. You are floating above a grand, turning wheel of silver and deep red, spiraling silently in the dark. At the very center of this swirling disk, a profound transformation is occurring. The gas at the core has become so dense that it is now completely opaque. In the earlier, thinner stages of the cloud, the heat generated by the falling matter could simply radiate away into the coldness of space. But now, the core has built a thick, insulating blanket around itself. The thermal energy is trapped. As you focus your awareness on the center, you can feel the warmth beginning to radiate outward. The temperature at the core begins to climb drastically. From the freezing depths of 10 Kelvin, the center of this collapsing cloud rapidly heats up, reaching surface temperatures of 2,000 to 3,000 Kelvin. A protostar is born. To the naked human eye, this newborn protostar would be entirely invisible, cloaked within its thick cocoon of dark dust. Visible light simply cannot penetrate the density of the cloud. But if you were to perceive the universe through the gentle warmth of infrared light, just as the James Webb Space Telescope does, having launched in 2021 specifically to peer through these cosmic veils, you would see a brilliant glowing sphere radiating deep, ruby-red heat against the black canvas of space. When this protostar is restless, shedding its excess energy in spectacular fashion. As material from the disk spirals downward onto the young star's surface, powerful magnetic fields channel some of this gas outward, launching it from the star's north and south poles. These are known as Herbig-Haro objects, named after the astronomers George Herbig and Guillermo Haro, who independently studied them in the late 1940s. These twin bipolar jets of superheated gas shoot out into the dark at astonishing velocities, traveling anywhere from 200 to 1,000 kilometers per second. Imagine the sheer, silent power of these cosmic fountains, glowing like neon beacons as they carve through the surrounding mist, leaving beautiful, glowing shockwaves in their wake. Yet, for all this immense heat and activity, the object at the center is still not truly a star. It has entered a prolonged adolescence known as the T-Tauri phase. This stage is named after the very first variable star of its kind, discovered in 1852 in the constellation of Taurus. During the T-Tauri phase, the protostar shines brightly, but it is not powered by nuclear reactions. Instead, its heat and light are generated entirely by the friction of its own gravitational contraction. Gravity is simply squeezing the star, wringing light out of the pressure. For millions of years, the young T-Tauri star continues to contract, and the temperature at its very core climbs higher and higher and higher. It is pushing toward a highly specific, magical threshold. For true starlight to spark in the universe, the core temperature must reach exactly 10 million degrees Kelvin. When that unimaginable temperature is achieved, a profound shift occurs in the very fabric of the atoms. The thermal kinetic energy is now so immense that the natural electromagnetic repulsion between hydrogen atoms is utterly defeated. The protons, which normally push away from one another like opposing magnets, are slammed together. This is the dawn of the proton-proton chain reaction. 4 individual hydrogen nuclei fuse together in a complex, beautiful atomic dance to create a single nucleus of helium. In this miraculous process, a tiny fraction of the original mass is lost. But according to Albert Einstein's elegant equation, E equals mc squared, that missing mass is converted entirely into pure, radiant energy. Consider the sheer scale of this invisible alchemy. In a mature star like our own Sun, this exact fusion process converts approximately 4 million metric tons of physical matter into pure, brilliant energy every single second. Every second, a mountain's worth of mass dissolves into light, warming the planets, driving the winds, and ultimately, far down the line, feeding the green leaves of Earth. With the ignition of nuclear fusion, the newborn star breathes outward. The incredible outward pressure generated by the continuous nuclear explosions perfectly pushes against the crushing inward weight of the star's own gravity. This delicate, permanent standoff is called hydrostatic equilibrium. It is the defining characteristic of a living star. Floating in the quiet dark, you can almost sense this balance. It feels like a deep, vibrating hum of stability. The chaotic collapse is over, and the frantic squeezing of gravity has met its equal and opposite force. The star settles into a perfect, glowing sphere, breathing steady light out into the dark. It is a moment of profound cosmic peace, an intricate balance of forces that will endure for billions of years, wrapping the surrounding space in a warm, steady embrace. Bathed in the steady, newborn light of this perfectly balanced sphere, we can observe the immediate aftermath of creation. The turbulent collapse has ceased, replaced by a profound, humming stability. But the star is still wrapped in its thick natal cocoon of leftover gas and ice. To truly shine out into the galaxy, it must clear its surroundings. Picture a towering lighthouse on a jagged coast, its powerful beams sweeping through a dense, heavy sea fog, slowly driving the mist away to reveal the dark ocean. In a wonderfully similar way, the young star begins to project a continuous outward flow of charged particles, known as the stellar wind. This invisible, silent current rushes away from the star's surface at staggering speeds, traveling anywhere from 400 to 800 kilometers every single second. As this relentless wind washes over the surrounding space, it gently but firmly sweeps away the remaining shroud of the molecular cloud, finally revealing the glowing stellar body to the vastness of the universe. For countless generations, the light from these newly unveiled stars traveled silently across the void, eventually falling upon the retinas of humans standing on a small rocky planet. Tracing the history of how we came to understand this cosmic birth is a beautiful journey through human curiosity. Look closely at the night sky over Earth in the winter of 1656. The Dutch astronomer Christian Huygens was pointing a primitive, custom-built refracting telescope toward a glowing smudge in the constellation of Orion. He was observing the Orion Nebula, a magnificent stellar nursery situated approximately 1,344 light-years away from our solar system. Looking through his glass lenses, Huygens described the glowing gas as a gap, or a torn opening, in the dark canopy of the sky, believing he was peering through the blackness into a brighter, luminous realm beyond. Over a century later, this curiosity deepened profoundly. Deep within the English countryside during the late 1780s, the sibling astronomer duo of William and Caroline Herschel spent countless freezing nights mapping the sky. Utilizing a massive, 20-foot-long reflecting telescope, they meticulously cataloged over 2,500 of these glowing celestial patches. They classified them using the word nebula, which is simply the Latin word for cloud or mist. While they could map the shapes of these distant mists, the actual mechanics of how a star formed within them remained a complete mystery, locked away in the quiet dark. The true breakthrough in understanding stellar anatomy did not come from a larger telescope, but from a tiny piece of glass. In the year 1814, a German physicist named Joseph von Fraunhofer invented the modern spectroscope. By passing starlight through a precise glass prism, Fraunhofer was able to fan the white light out into its component colors, creating a wide, glowing ribbon of violet, blue, green, yellow, and red. But as he examined this rainbow, he noticed something completely unexpected. The ribbon of light was interrupted by hundreds of microscopic dark vertical lines, like a celestial barcode. These are now known as Fraunhofer lines. They are the specific shadows left behind when cooler atoms in a star's outer atmosphere absorb exact, specific wavelengths of light. For the very first time in history, humanity had a key to read the chemical fingerprints of the cosmos. By interpreting these dark lines, scientists realized that the stars were sharing their secrets across millions of miles of empty space. Consider the solar eclipse of 1868. The French astronomer Pierre Janssen aimed his spectroscope at the glowing edge of our sun and discovered a bright yellow spectral line that matched no known element on Earth. He had discovered an entirely new element in the atmosphere of a star before it was ever found on our own planet. It was appropriately named helium, derived from Helios, the ancient Greek god of the sun. Yet, the most profound revelation about the birth and composition of stars arrived in 1925, penned by a brilliant astronomer named Cecilia Payne-Gaposchkin. In her doctoral thesis, now regarded as one of the most brilliant in the history of astronomy, she analyzed the light spectra of thousands of stars. She mathematically proved that, contrary to the scientific consensus of the time, stars were not made of heavy, rocky materials like the Earth. Instead, she revealed that the universe is overwhelmingly dominated by the lightest elements. The newly born star we are observing, and indeed almost every star in the sky, is composed of roughly 73% hydrogen and 25% helium. with only traces of heavier elements woven through the glowing gas. Now, understanding the heritage of this light, bring your focus back to the newborn star, resting in the dark. It has officially entered the most stable and enduring phase of its existence, known as the main sequence. This developmental stage was mapped out around the year 1910 by two independent astronomers, Einar Hertzsprung and Henry Norris Russell, who created the famous HR diagram to graph the life cycles of stars. The main sequence is a period of supreme comforting reliability. A star will spend approximately 90% of its entire total lifespan in this steady state, peacefully fusing hydrogen into helium in its core. But not all stars burn with the same intensity or color. The visual identity of our newborn star is governed by a principle of physics called Wien's displacement law, formulated by Wilhelm Wien in 1893. This elegant law dictates that a star's physical surface temperature directly determines its dominant color. If the molecular cloud had gathered only a small amount of material, it would birth a red dwarf, classified by astronomers as an M-type star. These small, gentle embers burn at a relatively cool surface temperature of 3,000 to 4,000 Kelvin. Because they sip their hydrogen fuel so incredibly slowly, a red dwarf can live for up to 10 trillion years. That is a span of time so unimaginably vast that not a single red dwarf formed since the dawn of the universe has ever died. They are the quiet, eternal watchers of the cosmos, glowing with a deep, soothing crimson warmth. Conversely, if the cloud had collapsed into an enormously massive body, it would ignite as a brilliant, fierce O-type blue giant. These colossal spheres burn at scorching surface temperatures exceeding 30,000 Kelvin. They are breathtaking to behold, glowing with a crisp, piercing sapphire light, but their lives are fleeting. They consume their core fuel with such voracious speed that they will exhaust their energy in just a few million years, a mere blink of an eye on the cosmic clock. Regardless of its color, our newly born star now settles into the slow, majestic rotation of the galaxy. But within this quiet clockwork, there is a hidden, rhythmic phenomenon that beats like the very heart of the universe. In the year 1908, an astronomer named Henrietta Swan Leavitt was studying photographic glass plates at the Harvard College Observatory. She noticed a specific class of stars, known as Cepheid variables, that did not shine with a constant light. Instead, they brightened and dimmed in a highly predictable repeating rhythm. Leavitt discovered that the exact length of this pulsing cycle was directly tied to the star's true luminosity, providing humanity with the first reliable standard candle to measure unimaginable distances across the deep universe. What is happening physically to these pulsing stars is an astonishing display of stellar mechanics. They are literally breathing. The entire outer envelope of a Cepheid variable star physically expands and contracts, swelling outward and shrinking inward by millions of kilometers with each breath. This magnificent cosmic heartbeat is driven by something known as the Kappa mechanism. Deep within the star's outer layers, a blanket of doubly ionized helium atoms acts as an atmospheric valve. When the star contracts, this helium layer compresses and becomes highly opaque, trapping the immense heat radiating from the core. The trapped heat causes the pressure to build, forcing the star's outer layers to push outward, physically expanding into space. As the star swells, the helium blanket expands, cools down, and becomes transparent once more. The trapped heat is suddenly released out into the comforting void in a brilliant flash of starlight. With the pressure relieved, gravity gently pulls the outer layers back down, and the cycle begins anew, expanding and contracting, dimming and brightening, inhaling and exhaling. Watching this rhythm, you can align your own quiet awareness with the slow, deliberate pulse of the ancient light. It is a perfect, the enduring cycle of physics, a testament to the quiet harmony established when a star is born, echoing across thousands of light years, waiting patiently for a telescope, a prism, and a human eye to finally read its glowing story. Resting quietly in this cosmic balance, we can now peer beneath the glowing surface of this newborn star to understand the hidden clockwork of its interior. Deep within the architecture of a main sequence star, the structure is elegantly divided into 3 distinct layers, functioning much like a monumental, self-regulating engine. The innermost sanctum is the core, taking up merely 20 to 25% of the star's total radius. Yet, this relatively small center holds an astonishing secret. When the matter here is crushed by the weight of the entire star into a state of plasma with a density of 150 grams per cubic centimeter. To ground this in everyday experience, that is exactly 150 times denser than liquid water on Earth, and nearly 10 times denser than solid lead. Picture a standard 1-gallon milk jug resting on your kitchen counter. If you could somehow fill that ordinary plastic jug with plasma scooped directly from the core of a star, it would weigh an incredible 1,250 pounds, likely crushing the table beneath it. Despite this immense, almost unfathomable density, the extreme heat keeps the material acting as a fluid, humming with the steady rhythm of atomic fusion. What is happening now is the slow, arduous journey of light itself. When a photon of light is forged in the nuclear furnace of the core, it does not simply shoot out into the empty void. Instead, it enters the second layer of the star, the radiative zone. This zone extends from the edge of the core out to about 70% of the star's radius. Notice how dense and crowded this region is. The newly born photon travels at the absolute speed limit of the universe, yet it can only move a fraction of a millimeter before colliding with a heavy plasma particle. It is instantly absorbed and re-emitted, bouncing off in a completely random direction. Astrophysicists map this erratic path using a mathematical model aptly named the random walk. Imagine trying to navigate your way out of a tremendously dense, dark forest, but every time you take a single step forward, you bump into a tree and are spun around to face a new direction. Because of this beautifully chaotic zigzagging, it takes a single photon anywhere from 100,000 to 170,000 years just to migrate from the core to the outer layer of the star. The soft, gentle starlight you see when you look up at the night sky was actually created millennia before humans ever learned to write, spending eons slowly tumbling outward through the interior maze of its own sun. Once the photon finally escapes the radiative zone, it arrives at the final internal layer, the convective zone. Here, the temperature drops just enough that the plasma becomes slightly more opaque, trapping the heat rising from below. Consider a heavy pot of thick soup simmering gently on a stove. As the burner heats the bottom of the pot, the liquid warms, expands, and bubbles up to the surface. Upon reaching the top, it meets the cool air, releases its heat as steam, and then slowly sinks back down to the bottom to be warmed again. The outer 30% of a star operates on this exact same principle of fluid dynamics. Colossal columns of superheated plasma, some wider than the entire planet Earth, rise to the star's surface. They release their trapped light out into the dark, cool off, and then plunge back down into the depths. This churning, rolling motion creates a textured, beautifully patterned surface called solar granulation, making the face of the star look like a vast simmering mosaic of golden cells. At this very moment, as the star boils and shines, it is also spinning. Because the star is not a solid, rigid object like a rock, but rather a sphere of fluid plasma, it undergoes a mesmerizing process known as differential rotation. Your scientists discovered the mechanics of this planetary scale twist in the 1850s, when an English astronomer named Richard Christopher Carrington dedicated his nights to meticulously sketching the movement of dark sunspots across the face of our sun. Carrington realized that the spots near the star's equator were moving significantly faster than the spots near the top and bottom. We now know that the equator of a typical yellow dwarf star completes a full rotation every 25 Earth days, while the poles drag behind, taking up to 35 days to complete a single turn. Imagine holding a thick, wet towel and gently twisting the top and bottom in opposite directions. Inside the star, this differential rotation rings and stretches the star's internal magnetic fields. The magnetic lines of force become wound up tighter and tighter over the years, wrapping around the star like coiled springs. This magnetic tension acts as a vast cosmic dynamo, quietly driving the elegant looping arcs of plasma that occasionally blossom far above the star's surface. While the star establishes its internal rhythms, a quieter, equally beautiful process unfolds in the surrounding dark. We must look outward to the leftover material, the thin spinning plateau of the protoplanetary disk that still circles the newborn sun. This disk contains only about 1% of the original molecular cloud's mass, but it is precisely from this tiny fraction of leftover dust and gas that entire planetary systems are born. In the extreme vacuum of space, microscopic grains of silicate and ice begin to collide. However, they do not smash together violently. Because they are moving in the same direction, be caught in the gentle current of the disk, they bump into each other softly. They stick together through weak electromagnetic attractions, called van der Waals forces. You can witness this same physics at work in the quiet corners of your own home. Underneath a bed or behind a bookshelf, tiny particles of dust, dead skin, and fabric fibers drift on microscopic air currents. Through the static cling of van der Waals forces, they slowly gather and bind together, creating soft, weightless dust bunnies. In the deep cosmos, this identical mechanism of gentle static cling is called coagulation. Over thousands of years, these microscopic stellar dust bunnies grow into pebbles. The pebbles gently clump into boulders, and the boulders gradually merge to form massive orbiting bodies known as planetesimals. The architecture of this emerging solar system is determined by a strict, invisible boundary known as the frost line or the snow line. For a star roughly the size of our sun, this thermal boundary sits approximately 5 astronomical units away from the center. Inside this line, the radiation from the newborn star is simply too intense for volatile compounds, like water, ammonia, and methane, to remain frozen. They vaporize, leaving behind only the heavy, heat-resistant elements, iron, nickel, and rock. This is why the inner planets of our own solar system, like Venus and Earth, are dense, solid, and rocky, but cross over the frost line, and the temperature of space drops precipitously below 150 Kelvin. Out here in the quiet deep freeze, water remains perfectly solid. Millions of tons of ice crystals act as cosmic glue, allowing the gathering planetesimals to grow to enormous proportions. These icy cores become so incredibly massive that their gravity begins to sweep up the abundant hydrogen and helium gas left in the disk, swelling into magnificent swirling gas giants like Jupiter and Saturn. Yet, as we trace the elegant mechanics of solar systems, it is worth acknowledging that not every collapsing cloud achieves this brilliant destiny. Sometimes, the fragment of gas pulling away from the nebula is simply too small. Picture a campfire where you have arranged the logs perfectly, but you only have a single damp match. You strike it, the wood smolders and warms, but it never truly catches fire. In the universe, if a collapsing core gathers less than roughly 80 times the mass of the planet Jupiter, its internal pressure will never be strong enough to force regular hydrogen atoms to fuse. These objects are known as brown dwarfs. The first undisputed brown dwarf was only recently confirmed by astronomers in 1995. Located about 400 light-years away in the Pleiades star cluster, it was given the name Tide 1. A brown dwarf is often called a failed star, but there is a profound, quiet dignity to its existence. While it lacks the immense crushing weight to ignite regular hydrogen, it can briefly fuse a rare, heavier isotope called deuterium. For a few million years, it glows with a very faint, deep magenta heat, but eventually, the deuterium runs out. Without the sustained nuclear engine of a true star, the brown dwarf slowly, gently cools down. It becomes a silent, wandering traveler in the cosmic dark, hovering somewhere between the heaviest of planets and the lightest of stars, radiating only a whisper of infrared warmth as it drifts endlessly through the comforting void. Stepping away from the quiet, wandering paths of the brown dwarfs, we return our gaze to the brilliantly successful main sequence star, burning steadily in the dark. While it may seem distant and separate from your life on Earth, the glowing sphere before us is actually intimately connected to your very existence. To understand this profound relationship, we must look far into the future of this star, to the legacy it will eventually scatter into the deep. Deep inside the fiery core, the star is acting as an immense cosmic factory. In the year 1920, the renowned British astrophysicist Arthur Eddington was the first to propose that stars draw their energy by fusing simple hydrogen into helium. But the process does not stop there. Once a star eventually exhausts its primary hydrogen fuel, the core contracts, the temperature skyrockets, and the star begins to forge completely new, heavier materials. Picture a master weaver seated quietly at a massive ancient loom. At first, the weaver only works with the simplest, lightest threads, the raw hydrogen left over from the very dawn of time. But as the years pass and the pressure mounts, the weaver begins to pull these simple threads together, intertwining them to create increasingly complex and heavy patterns. This delicate atomic weaving is known as stellar nucleosynthesis. One of the most crucial patterns on this cosmic loom is the creation of carbon, the fundamental building block of all known biology. Astrophysicists trace the origin of this element back to a mechanism called the triple alpha process. In 1954, the astronomer Fred Hoyle theorized that for carbon to exist in the universe, 3 separate helium nuclei must collide almost simultaneously inside a dying star. This is an incredibly precarious dance. When the first 2 helium nuclei fuse, they form an unstable isotope called beryllium-8. This fragile isotope has a lifespan of merely a 10 quadrillionth of a second, written out as 10 to the power of -16 seconds. Before that fleeting fraction of a moment expires, a third helium atom must strike the beryllium perfectly, fusing together to lock the structure into stable carbon. Reflecting on this impossibly precise atomic choreography, brings a profound sense of grounding. Every single carbon atom currently resting in your body was woven together in this exact, fleeting collision inside the furnace of an ancient sun. By mass, the human body is approximately 18% carbon. That material did not originate on Earth. It was delivered here. As the star ages, the weaver at the loom continues to build heavier elements through a sequence called the alpha ladder. By adding more helium nuclei to the chain, the star forges oxygen. Oxygen is the single most abundant element in your physical form, making up roughly 65% of your body mass. As you rest quietly now, feeling the slow, rhythmic rise and fall of your chest, and you are continuously drawing in oxygen atoms that were forged billions of years ago in the deep, silent heart of a star. Think about the structure supporting you as you lie here, the skeleton resting comfortably against the mattress. The calcium within your bones is yet another product of this stellar alpha ladder. And deeper still, flowing through your veins, is iron. The iron molecules at the center of your hemoglobin, the tiny structures that carry the oxygen through your bloodstream, are forged only in the absolute most extreme conditions imaginable. For a star to weave iron, its core temperature must reach a staggering 2.5 billion Kelvin. It is the final, heaviest element a standard star can produce before its core collapses. Scientists calculate that a single adult human body is composed of approximately 7 octillion atoms, and that is a 7 followed by 27 zeros. Astoundingly, 97% of the mass of those atoms consists of stardust, elements cooked in the bellies of ancient stars, eventually expelled into the comforting void through slow stellar winds or majestic supernova explosions. You are not simply an observer of the universe. You are a complex, conscious piece of it, quietly experiencing itself. To witness how this stardust eventually finds a home, we return to the spinning disk of material orbiting our newborn star. As the planets slowly gather their mass, a delicate concept comes into play: the habitable zone. In 1959, an astrophysicist named Sushu Huang formally coined this term to describe the highly specific ring of space around a star where conditions are perfectly balanced. It is often affectionately called the Goldilocks zone. Within this precise boundary, the temperature of space is not so scorching that water boils away into vapor, nor is it so frigid that it locks into permanent ice. It is the exact orbital distance where water can exist as a gentle, flowing liquid on the surface of a rocky planet. Our own Earth sits comfortably within the habitable zone of our Sun, a star that formed 4.6 billion years ago, with the Earth coalescing from the dust roughly 100 million years later. Finding these perfectly placed planets in the wider universe is a triumph of modern patience. The very first confirmed discovery of an exoplanet orbiting a sun-like star occurred in 1995, achieved by Swiss astronomers Michel Mayor and Didier Queloz. They detected a massive planet named 51 Pegasi b, located about 50 light-years away from Earth. Remarkably, this giant world completes an entire orbit around its host star in just 4.2 Earth days. While 51 Pegasi b is far too close to its star to hold liquid water, its discovery proved that the intricate clockwork of solar systems we see around us is repeating endlessly throughout the dark. Furthermore, a star does not merely create the materials for life. It actively shields and protects the planets that circle it. Moving outward from the central fire, the steady stream of charged particles pouring off the star's surface creates an immense invisible bubble in space known as the heliosphere. Visualize this heliosphere as a colossal, translucent shield enveloping the entire solar system. As the star journeys through the dense, colder interstellar medium of the galaxy, this magnetic bubble pushes back against the surrounding void. It acts as a necessary barrier, deflecting high-energy galactic cosmic rays that would otherwise strip away the delicate atmospheres of the inner planets. We know the exact boundaries of our own sun's protective bubble, thanks to humanity's furthest emissary. In August of 2012, the Voyager 1 space probe, launched decades earlier in 1977, officially crossed the heliopause, the very outer edge of this protective shield. Instruments aboard the small, silent craft recorded the crossing at an astonishing distance of approximately 121 astronomical units from the Sun. As Voyager slipped into interstellar space, it detected a sudden, dramatic shift in the environment. The plasma density of space spiked, jumping up to roughly 0.08 atoms per cubic centimeter, confirming that the probe had finally left the warm, protected harbor of our star and entered the true deep ocean of the galaxy. Even closer to home, this relationship between stellar energy and planetary protection creates some of the most beautiful phenomena in nature. When the steady, invisible stream of our sun's charged particles reaches Earth, it encounters our planet's own internal magnetic field, the magnetosphere. The Earth gently guides these solar particles away from the surface, channeling them toward the magnetic north and south poles. As these charged cosmic travelers collide with the gases in our upper atmosphere, they transfer their energy in a breathtaking display. When the solar particles strike oxygen molecules high above the Earth, they emit a soft, glowing light in shades of pale green and deep red. When they collide with nitrogen, they paint the night sky in vibrant ribbons of blue and purple. This is the aurora borealis and the aurora australis, a quiet, luminous reminder of the constant invisible conversation occurring between a star and its planets. Resting in the dark, you can find profound peace in these connections. The universe is not a chaotic, random scattering of matter, but a deeply interwoven system. The heavy elements that form the solid ground beneath your home were forged in a star. The oxygen filling your lungs as you breathe was crafted in the intense, glowing core of a giant. The magnetic fields that protect your atmosphere hold back the deep cold of space, allowing life to flourish in a delicate, protected warmth. There is an enduring comfort in knowing that the slow, massive physics of the cosmos are directly responsible for the quiet sanctuary you are experiencing right now. The same forces of gravity that pull a molecular cloud together are the very forces keeping you securely anchored to your bed. The same laws of thermodynamics that govern the slow cooling of a planetary surface are allowing your body to regulate its own temperature as you rest. You are beautifully, inextricably bound to the clockwork of the stars. Observe how the celestial environment holds a profound, invisible richness. As we hover gently in the quiet space surrounding our newborn star, we can explore an unexpected question driven by deep scientific curiosity. What does this cosmic nursery actually smell like? To understand this, we must look at the complex chemistry floating in the spaces between the stars. In the year 2009, astronomers aimed the massive IRAM 30-meter radio telescope, located high in the Spanish Sierra Nevada, toward a giant molecular cloud known as Sagittarius B2. This magnificent cloud sits near the very center of our Milky Way galaxy, spanning a breathtaking 290 light-years across. By analyzing the radio waves absorbed by the gas, the scientists detected the undeniable signature of a specific organic molecule called ethyl formate. The presence of this chemical is highly revealing. On Earth, ethyl formate is the exact ester responsible for giving raspberries their sweet, tart scent, and it is the same compound that provides rum with its distinct, deep aroma. Furthermore, these interstellar clouds are laced with polycyclic aromatic hydrocarbons, or PAHX. These are complex, ring-shaped carbon molecules that, if you could safely breathe them in, would smell remarkably like burnt toast or the lingering smoky scent of a struck match. You might ask why these complex, fragrant molecules exist in the freezing void. The answer lies in the microscopic textures of the cosmic dust. In the deep cold of space, a tiny grain of silicate dust acts as a floating anvil. When individual atoms of carbon, hydrogen, and oxygen drift through the vacuum and strike this microscopic surface, they stick. Over thousands of years, the surface of the dust grain catalyzes a reaction, allowing these atoms to bond together into complex organic chains. The surrounding space is not merely empty, it is a fragrant chemical sea, laced with the building blocks of sweetness and smoke. Listen closely with the instruments of modern astrophysics, and you will discover another astonishing sensory detail. Stars are not silent. While sound cannot travel through the vacuum of space, the interior of a star is completely filled with ultra-dense plasma, providing a perfect medium for acoustic waves. The study of these stellar vibrations is a fascinating field known as asteroseismology. Deep within the star's boiling convective zone, the violent churning of plasma creates continuous, deafening, low-frequency sound waves. Physicists call these pressure waves, or P-modes, because the internal density of the star is so unimaginably high. These sound waves travel at blistering speeds, tearing through the solar interior at nearly 1 million miles per hour. As these acoustic waves bounce around inside the star, they interfere with one another. You're canceling out some frequencies while amplifying others. Picture a colossal spherical bell made of liquid gold, continuously struck by the internal hammer of its own boiling heat. The star actually rings. We cannot hear this grand cosmic symphony with our ears, but we can see the physical rhythm it creates. In 1960, the American physicist Robert Layton discovered what is now known as the 5-minute oscillation. The acoustic waves trapped inside a sun-like star cause the entire physical surface of the sphere to rhythmically heave outward and sink inward. Every 5 minutes, the face of the star rises and falls by approximately 3,000 meters. As you observe the glowing sphere before you, you are watching it physically breathe, expanding and contracting to the beat of an ancient, trapped vibration. Gaze upward from the star's surface, and the visual textures shift dramatically. Resting immediately above the blinding yellow photosphere is a thin, delicate layer of the star's atmosphere, known as the chromosphere. The name originates from the Greek word chroma, meaning color, because this layer emits a stunning ruby red light. The physics behind this specific hue are rooted in the Balmer series, a set of mathematical formulas describing the emission of light from hydrogen atoms. When the electrons within the superheated hydrogen fall from their third energy level down to their second, they release a photon at an exact, unchangeable wavelength of 656.28 nanometers. This specific measurement, known as the hydrogen alpha line, bathes the entire chromosphere in a deep, soothing crimson glow. Through a specialized telescope, the texture of this crimson layer is mesmerizing. In 1877, the Italian astronomer Father Angelo Secchi carefully observed the edge of the sun and documented thousands of tiny hair-like structures shooting upward. He named them spicules. These are massive supersonic jets of magnetic plasma that erupt continuously from the star's surface. A single spicule can stretch 10,000 kilometers high, nearly the diameter of the entire planet Earth, and lasts for only about 10 minutes before collapsing back down. From a distance, the chromosphere looks just like a vast curved prairie of fiery red grass, gently swaying and rippling in a silent magnetic breeze. Rising even further outward, we encounter one of the most compelling mysteries of stellar physics, the corona. This is the star's outermost atmosphere, stretching millions of miles into the dark. Curiously, as you move further away from the star's heat source, the temperature does not drop. Instead, it violently spikes. The surface of a yellow dwarf star rests at a relatively stable temperature of 5,800 Kelvin. Yet, if you measure the halo of the corona directly above it, the temperature rockets upward to anywhere between 1 and 3 million Kelvin. This brilliant paradox is known as the coronal heating problem. How can a campfire be infinitely hotter 10 feet away than it is at the actual coals? In 1988, the visionary astrophysicist Eugene Parker proposed an elegant solution known as the nanoflare theory. Parker theorized that the star's magnetic field lines are constantly twisting, braiding, and snapping like invisible rubber bands under immense tension. When these magnetic lines snap and reconnect, they release tiny, invisible bursts of energy. Because millions of these microscopic nanoflares are detonating every single second across the entire star, they collectively superheat the upper atmosphere to millions of degrees. Despite this blistering temperature, the sensory reality of floating within the corona is entirely counterintuitive. If you could hover inside this 3 million degree halo without a spacesuit, you would not burn. You would instantly freeze. The reason for this lies in the difference between temperature and heat. Temperature is simply a measurement of how fast individual particles are vibrating. In the corona, the protons and electrons are moving at frantic, tremendous velocities, giving them an incredibly high temperature. But heat is the actual transfer of energy, which requires density. The corona is a near-perfect vacuum, containing roughly 1 billion particles per cubic centimeter. While that sounds like a large number, it is billions of times less dense than the air in an empty room on Earth. Because the particles are so incredibly far apart, there are simply not enough of them striking your skin to transfer their thermal energy. The space is mathematically boiling, yet physically, texturally, it remains a profound, freezing void. Underpinning all of these magnificent sensory details, the scent of the molecular clouds, the deep 5-minute ringing of the surface, the red swaying spicules, and the freezing heat of the corona is a slow, majestic cycle of time. Stars are not static objects. They operate on a deep, predictable, and rhythmic clock. In the year 1843, a German pharmacist and amateur astronomer named Heinrich Schwabe published the results of 17 years of daily solar observations. He had patiently counted the dark sunspots dotting the surface of our sun and realized they followed a strict repeating rhythm. This became known as the Schwabe cycle, an 11-year period over which a star's magnetic activity slowly rises to a chaotic peak and then gradually relaxes into a soothing, quiet minimum. At the peak of this 11-year cycle, the star's magnetic field becomes so incredibly tangled by its own rotation that it physically breaks and flips. The magnetic North Pole becomes the South Pole, and the South becomes the North. This immense magnetic inversion happens softly and silently, regulating the flow of the star's energy. Here, watching this rhythm unfold brings a deep sense of order to the cosmos. The star breathes its acoustic waves every 5 minutes. The spicules rise and fall every 10 minutes. The magnetic poles flip every 11 years. The light itself takes 100,000 years to wander from the core to the surface. Everything is tied to a specific, beautifully balanced tempo. As we drift above this swaying prairie of glowing plasma, bathed in the warmth of the hydrogen alpha light, we can appreciate the profound clockwork mechanics required to maintain it. It is an environment built on precise mathematics and vast atomic forces, yet it results in a soothing, reliable beacon. The invisible scents of raspberries and match smoke drift outward on a solar wind made of protons, moving at 400 kilometers per second, carrying the signature of the star's birth far into the quiet reaches of the galaxy. Shift your perspective away from the glowing surface of the newborn star and allow your awareness to slowly drift outward, capturing the grander choreography of the galaxy. The birth of this star is not an isolated event, but the beginning of a majestic, sweeping journey. We can now observe the step-by-step process of how a star and the planets that circle it integrate into the wider clockwork of the cosmos. The sequence begins as the star gradually leaves its natal cloud, entering a vast, quiet cavity in the interstellar medium known as the local bubble. Astronomers have mapped this enormous hollow structure, revealing it to be roughly 1,000 light-years wide. It was slowly carved out over millions of years by the shock waves of ancient supernovae. Moving into this space is an incredibly peaceful transition, because the local bubble is remarkably empty. The density here is extraordinarily sparse, containing merely 0.05 atoms per cubic centimeter. It is a quiet, frictionless ocean for the young star to sail through. Next, the star finds its gravitational footing within the swirling disk of the Milky Way. It locks into an orbital path around the galactic center. This is not a rapid journey. A star like our Sun glides through this space at a smooth, steady velocity of about 220 kilometers per second. Even at this tremendous speed, the sheer scale of the galaxy requires 225 to 250 million Earth years to complete a single orbit. Astrophysicists refer to this massive span of time as one galactic year. It is a slow, enduring marathon. The physical matter that makes up your body has completed this grand circle around the galaxy roughly 20 times since the Earth first gathered its shape from the dust. Focusing gently on that rocky planet, we can trace the precise mechanics of nightfall. The experience of darkness on Earth is entirely governed by the conservation of angular momentum established billions of years ago in the protoplanetary disk. As the planet spins, the side facing away from the star plunges into shadow. This rotation is not perfectly constant, due to the steady, rhythmic tidal friction caused by the gravitational pull of our moon. The Earth's rotation is gradually decelerating. Over time, the length of an Earth day slowly stretches, increasing by exactly 1.8 milliseconds every single century. Observe how the sunset unfolds in a beautiful, mathematical sequence. As the star dips below the physical horizon, the Earth's atmosphere scatters the remaining light. But eventually, the exact wavelength of 480 nanometers vanishes from the sky. This specific measurement of light corresponds to the bright blue of daytime. The gradual removal of this blue light from your environment acts as the absolute first step in a brilliant biological cascade, directly linking the turning of the planet to the architecture of your brain. When the 480 nanometer light ceases to strike the human retina, a quiet signal travels deeply into the brain arriving at a tiny paired structure called the suprachiasmatic nucleus, nestled within the hypothalamus. This small cluster of cells acts as your body's master clock. Step by step, the suprachiasmatic nucleus processes the absence of starlight and sends a message to the pineal gland. The history of understanding this tiny gland is a journey of human wonder. In the year 1662, the French philosopher and scientist René Descartes meticulously studied the pineal gland, proposing it was the literal seat of the soul, the exact location where human consciousness interacted with the physical body. Today, modern endocrinology reveals a reality that is equally profound. The pineal gland responds to the darkness by synthesizing and releasing a critical hormone called melatonin directly into your bloodstream. As the melatonin circulates, the next phase of the sleep sequence begins. The cardiovascular system gently adjusts, diverting blood flow away from the core and toward the extremities. Then this physical process allows your body's internal core temperature to steadily drop by roughly 1 to 2 degrees Fahrenheit. This internal cooling perfectly mirrors the slow cooling of the Earth's crust as the night progresses. You are harmonizing with the thermal rhythm of the planet. Simultaneously, a profound chemical clearing occurs within your cells. Throughout your waking hours, your body operates by consuming a molecule called adenosine triphosphate, or ATP, for cellular energy. When ATP is broken down, it leaves behind a byproduct molecule called adenosine. As adenosine slowly builds up in the brain, hour by hour, it binds to specific receptors, creating the gentle, undeniable physical pressure of sleepiness. To create that ATP energy, your body relies absolutely on the element phosphorus. Here, the deep connection to the cosmos reveals itself once more. The phosphorus currently regulating your cellular energy was forged inside massive stars during a specific stage known as oxygen and neon fusion, requiring an unimaginable core temperature of over 1 billion Kelvin. The heavy elements crafted in those ancient fiery depths are now quietly facilitating your ability to rest. The process deepens as your brain transitions away from the frantic beta waves of the day, moving softly into the realm of slow wave sleep. This stage is characterized by delta waves, which gently undulate at a remarkably low frequency of 0.5 to 4 Hertz. During this deep neurological rhythm, the brain begins removing cellular byproducts, organizing memories, and repairing tissues. This repair is managed by the intricate movement of ions, particularly calcium. Calcium ions flow through tiny synaptic channels in your brain, triggering the release of an inhibitory neurotransmitter called GABA, which effectively quiets the nervous system. Every single atom of that calcium was created in the dying explosion of a supernova. You are utilizing the ashes of a destroyed star to find peace in the dark. Furthermore, recognize the physical water making up roughly 60% of your body mass, quietly regulating your temperature and supporting this chemical cascade. The hydrogen within that water is the oldest material in your possession. It was not formed in a star. Instead, astrophysicists trace the origin of all hydrogen back to an era known as the recombination epoch, which occurred exactly 380,000 years after the Big Bang. At that moment, the universe finally cooled enough for the very first protons to capture electrons. You are resting with the primordial fabric of the universe flowing through your veins. As you lie here in the quiet, the boundary between your physical form and the wider cosmos is wonderfully porous. The biological clockwork continues. Every single hour, the human body naturally sheds roughly 200 million microscopic skin cells. Step by step, the stellar carbon and ancient oxygen that once burned brightly in the deep void are quietly released from your body, returning to the surface of the earth to become soil, air, and eventually, new life. You are a temporary, beautiful gathering of cosmic material, organized into a state of profound awareness. And right now, that awareness is allowed to dim, to cool, and to rest. The sequence of the night is unfolding exactly as it should. The star holds its orbit in the local bubble. The planet turns its heavy, quiet face into the dark. The blue light fades. The melatonin rises. The temperature drops. The delta waves slow down to a gentle, sweeping hum. Embrace the silence of the comforting void. The universe is endlessly patient, and it is holding you securely in its vast, invisible web of gravity and warmth. I am made of ancient light. My chemistry is perfectly balanced by the laws of physics. I rest within the deep, slow time of the galaxy. The rotation of the Earth brings me absolute peace. My body knows exactly how to quiet itself. I surrender my energy to the slow cooling of the night. The universe is a sanctuary of profound order. I am entirely safe in the dark. I release all tension into the steady pull of gravity. My mind slows down, mirroring the silent, freezing depths of space. I am connected to the elements that formed the world. I breathe in the quiet of the interstellar mist. I breathe out the exhaustion of the day. The clockwork of the cosmos is soothing, eternal, and kind. I allow my awareness to float endlessly in the dark. I am resting in the shadow of a star. I am a part of the quiet universe. I am completely at peace. Good night.